Nicole and Flores Reginaldo of Group 4, and now I'm going to discuss on how to use compound or connectives in creating compound statements. In psychology, you need to understand the differences, what you are using, simple and compound statement. Now, simple statement, it is to convey one idea with no connecting words, while compound statement, it is the statement which combine two or more simple statement using connectives. And the connectives we are using in this lesson, example of connectives and compound statement are and, or, if then, if and only if. These are the connectives that we are using in symbolic logic. Now, let's start our operation in AND statement, which is defined by conjunction. If P and Q are two simple statements, then the compound statement P and Q is symbolized by this symbol. And this symbol that you are seeing right now is the symbol that we use for two statements using the AND connectives, which is P symbolized by this and Q. Now, how do we use these particular connectives in operation in symbolic logic? Let's say we have two statements, which is it is 5 p.m. represented by the P. They are working represented by Q. And we are going to connect these two simple statements to make it compound statement, such as the two statements that you are seeing right now. So let's say we are going to transform the sentences or compound statement in symbolic form. Since AND is a connectives in symbolic logic represented by this symbol, we can write this sentence into P, this symbol, Q, using symbolic logic. So the example, it will form, it is after 5 p.m. and they are working, symbolized by P and the symbol. We are done with the AND statement. Now, we are going to discuss the OR statement, in which it is defined by this conjunction is a compound statement formed using the inclusive or represented by the symbol like this. Thus, P or Q both is symbolized by P, the symbol, and Q. Example of this OR statement, the bill received majority approval, represented by the P. The bill becomes the law, represented by the Q. So, it will form into the bill receives majority approval, or the bill becomes a law. And this statement will be represented by P, this symbol, and Q. So, this is how we use this symbol in connectives to create a compound statement. Why the bill receives majority approval or the bill becomes a law is represented by P, V, Q, because it can change it into symbolic form using the OR statement.
If and only if statement. Biconditional means that P implies Q, or P if only if Q. Example, let E, T, A, and G represent the following statement. E, all men are created equal. T, I am trading places. A, I get Ben's place. G, I get Anna's place. So, T implies G, or T if only if G. T, it is I am trading places. And G, I get Anna's place. So, gagawin natin siyang into sentence. I am trading places if and only if I get Anna's place. So, T, if and only if G.
Now, let's go on to the third connective that we are going to be using, which is the if-then statement. So, the compound statement if P then Q is symbolized by then Q, which we are seeing right now on our arrow going towards the second statement. So, in this particular statement, which is conditional statement, we have two different statements. One is the antecedent and the consequence, which means that just like an arrow that you are seeing on the first statement going towards the second statement. So, let's begin. Let P and Q represent the following statement. The P, a person is a father. Q, a person is a male. So, if we're going to represent the if-then symbol in this statement, starting for the first one, the statement we're gonna be is if a person is a father, then the person is a male. So, this actively means that if P, then Q can be formed by this particular symbol.
Conditionals and biconditionals featuring Jomar, Yesa, and Noella.
Conditional statements is one of the most frequently used type of statements in mathematics. It's symbolized by P and Q. It's the statements in which P it's a hypothesis and Q is a conclusion. The logical connector and conditional statements and donated by the symbols like this right painting arrow. Conditional statements are those statements where our hypothesis is followed by the conclusion and is also known as an if-then. Statements is a hypothesis is false, then the conditional statements is false. Likewise, is the hypothesis is false, then whole statements is false. In short, conditional statements set up conditions that could be true or false, which could also lead to a result that may or may not be true. For instance, if rains, then they are cancelled schools. But what if the rain for the days is not pouring that hard? Are they still going to cancel classes? It's for them to know and for us to find out see. These statements might be true, these statements might be true, but it can also be false. And as mentioned earlier, conditional statements consist of two parts, a hypothesis in the if clause and conclusion in the then clause. For example, if today is Wednesday, then yesterday was Thursday. The hypothesis in if today is Wednesday, so your conclusion must follow then yesterday was Thursday. If it hypothesis is if it is not raining, so your conclusion must follow then this is raining hereby. To verify statement are correct, we need to take a deeper look at your if-then statements, and in doing so, their types of conditional statements are from converse and inverse and contrapositive.
Sir, what is the converse, inverse, and corresponsive of a statement?
Well, the converse is when we switch or interchange your hypothesis and conclusion. If Q, then P. Now the inverse of by negating making negative, but the hypothesis and conclusion of the conditional statement. If not P, then not Q, and the contrapositive is formed by interchanging the hypothesis and conclusion, and then negative both. If not Q, then not P. Let us take a look at this sample of conditional statement. If I eat a lot, then I will gain weight. If we are going to write in it converse, I would be, if I gain weight, then I eat a lot. If I inverse from it would be, if I do not eat a lot, then I will not gain weight. And if we will write in contrapositive, from it would be, if I did not gain weight, then I did not eat a lot.
A biconditional statement is defined to be true whenever both parts of the same truth value. The biconditional operator is denoted by a double-headed arrow. The biconditional PQ represents P if and Q only if, where P is hypothesis and Q is conclusion. For example, I have triangle. If and only if my polygon has exactly 3 sides. Another, the polygon has only 4 sides. If and only if it is a quadrilateral. Reminder this, a biconditional statement is a statement combining conditional statement with its converse. So, when conditional is true, if and only if the other one is true as well. It often uses the word if and only if, or the shorthand if. It uses the double arrow to remind you that the conditional must be true in the both direction. It is a logical conditional statement in which the antecedent and consequent are interchangeable. Now, how can write a biconditional statement? Let us watch this video.
A conditional statement is an if-then statement. If blank happens, then blank will happen. For example, if you study your math, then you'll get a good grade. Okay. Now what the converse is, it's you switch the two, the hypothesis and the conclusion. Whatever comes after the if is the hypothesis, whatever comes after the then is the conclusion. But when you switch those, we call this the converse. Now, if the conditional statement is true and the converse statement is also true, the way I like to think about it is if you say it forwards and then in reverse or backwards, the converse, if they're both true, both those statements, then that means you can write it as a biconditional statement. Bi meaning two, conditional meaning if then, okay? And we can symbolize this with a double arrow. So if P, if and only if Q, or Q, if and only if P. And that's how you want to write your biconditional statement. What you do is, if it's true forwards and reverse, meaning the conditional and converse are both true, you drop the if and you replace the then with this phrase, if and only if. Okay, and so what that does is it tells the reader, meaning you and me, that it's true forwards and in reverse. So let's do an example. So if a triangle has an angle measure that's greater than 90 degrees, then it is an obtuse triangle. So just a quick visual here, say you have a triangle and this angle is 120 degrees, then we would call this triangle an obtuse triangle, right? Okay, but now here's the thing. Whatever comes after the if, okay, meaning a triangle has an angle measure greater than 90, that's our hypothesis. Whatever comes after the then, that's our conclusion, right? So is this true? If a triangle has an angle measure greater than 90, then it's an obtuse triangle? Yes, that's true. But now what we're going to do is we're going to switch the hypothesis and the conclusion and see if that's also true. So let's say it in reverse. So if a triangle is an obtuse triangle, then the triangle has an angle measure greater than 90 degrees. Is that true? Yes, that is true as well. So what that means is that we can write this as a biconditional statement, and here's how we're going to do it. We're going to drop the if, and we're going to replace the then with this phrase, if and only if. So here it goes. A triangle has an angle measure greater than 90 degrees if and only if it is an obtuse triangle. Okay, we got it. So let's do a second example. It says a number is rational if and only if it can be written as a ratio of two integers. Okay, so just a quick review in case you don't know about rational numbers. See this word rational? Rational just means it can be written as a ratio, meaning a fraction of an integer divided by another integer. Okay, so for example, 2/3, that's rational because it's an integer over an integer. Say for example, square root of 16, that's equal to 4, which is like 4 over 1. That's a ratio of an integer over an integer. So let's read this again. So they're telling us it's a biconditional statement. See this if and only if? That tells us that it's true forwards and in reverse. So let's break it down into its original conditional statement and its original converse statement, okay, before we put it together into this biconditional. So how about first, if a number is rational, then it can be written as a ratio of two integers. Okay, let's do the converse now. If a number can be written as the ratio of two integers, then it is a rational number. So you see how if we're given a biconditional, we know that it's going to be true forward and the converse. I like to say it like in reverse, backwards, but what we're doing is we're switching the hypothesis and the conclusion. So remember, conditional statements are if-then statements, but when you write a biconditional, you drop the if, you place the then with if and only if.
Did you get the process? We're just going to make sure that the but conditional statement and its converse that we are going to use are all stating a fact.
Ma'am, sir, is there any difference between conditional and biconditional statements?
Yes, there is. As noun, the difference between conditional and biconditional is that conditional is grammar, a conditional sentence. A statement that depends on a conditional being true or false, while being conditional is logic. An if and only if conditional, wherein the truth of each term depends on the truth of the other.
And as adjectives, the difference between conditional and biconditional. Thus conditional is limited by conditional, while biconditional is having two conditions.
A truth table is a mathematical table used in logic which sets out the functional values of logical expressions on each of their functional arguments, that is, for each combination of values taken by their logical variables. It is used to determine if a compound statement is true or false. In a truth table, each statement is typically represented by a letter or variable like P, Q, or R, and each statement also has its own corresponding column in the truth table that lists all of the possible truth values. To construct a truth table, we need to be familiarized with these types of statements and their connective symbols. In our topic, we have if-then connective with the right pointing arrow as a symbol for conditional, while if and only if connected with a double arrow symbol for biconditional.
We also have different guides in making truth table. We have one for conjunction, negation, disjunction, conditional, and biconditional. Let us take a look at these examples.
Example 1. Construct a truth table for if P, then not Q. The first thing that we're going to do is to negate the Q since it has the not sign. So we have T, it will become F for false, and so on, like FT, TF, then FT. After that, let us now get the value of this. The P and the not Q. Let us make this table for conditional as our guide in looking for the answers. So T, F is F, T, T is T, F, F is T, and ft is t. After doing all of that, here are now the final answer for example 1. We come now to the next example. Construct a truth table for if not P, then Q. Same as the number 1, we need to find the negation first. But in this sample, we're going to negate P. So we have T, F, T, magiging F, F, T, F, T. After that, proceed to the next. Get the answers by using this conditional table, Q and not P. T, F is T, F, F is T, T, T is T, F, T, F. So here's the answer for example number 2. Example 3, construct a truth table for P or if Q, then not P. Like the other example or like the previous ones, we're going to find the negation of P. So it would be T, F, T, F, F, T, F, T. After that, let us look for the truth value of the proposition inside the parentheses. It is a conditional, so we're going to use this conditional truth table as guide. T, F is F, F, F is T, T, T is T, F, T is T. So after that, after doing the negation in this solving for the conditional, we can now finally look for the truth value of this one using the disjunction as our guide. We're going to look at the P and the Q, not P column. So we have T, F is T, T, T is T, F, T, T, F, T, T. So we have here the final truth table for example number 3. Another, construct a truth table for if P, then Q. If and only if not P, then Q. So as you can see, we have here the biconditional and conditional symbol. So we're going to solve for these two. First, we're going to find the negation of P. So there it is, TF, TF, FT, FT. After that, we're going to find the first proposition, the truth value of the first one, which is inside the parentheses. If P, then Q. We're going to look at the P and Q column and use this conditional truth table as a guide. So we have here TT is T, TF is F, FT is T, FF is T. After that, let us get the second one, second inside the parentheses. But here we're going to look at the not P and Q. Remember to always look at the first or on which is the first one. So not P, Q. FT is T, FF is T, TT is T, TF is F. After solving all of this, we can now finally get or solve for the truth table of this, for example, number 4. Let us use the biconditional. TT is T, FT is F, TT is T, TF is F. So here's the truth table for example number 4. Last example, we have here, construct a truth table for P and Q. If and only if P, then not Q. So in this example, we have conjunction, biconditional, and conditional. Let us first find the negation of Q. As you can see, there it is, TF, FT, TF, FT. After that, let's look for the conjunction value. Let us use this conjunction truth table as the guide and look at P and Q. TT is T, TF is F, FT, F, FF is F. So after that, we can now proceed to the next column. If P, then not Q. Let us use the conditional truth table as our guide. We're going to look at the P and not Q column. TF is F, TT is T, FF is T, FT is T. So here we have, after answering all this, we can now finally move to the final column. Let us use the biconditional truth table as our guide. TF is F, FT is T, FT is F, FT is F. We can now have this truth table for example number 5.
Did you get the process? Just remember these guides to make a truth tables correctly.